Good day, class. It was last night that I have noticed that the recordings that I did for the second part for the sample problem uh, was cut. I don't know how it happened. So there were around more than 30 to 40 minutes of recording that was not recorded. So it ended, actually the recording ended with the illustration for the sample problem. So I will do it again today. That way your um, understanding of how the problem should be tackled, this is actually coming from Colson, should be complete. Okay, so we will redo. Anyway, what I have ended there in the previous recording is just the given information. So this is the plant that produces 100 kilograms per second of titanium dioxide pigment, which must be 99.9% pure when dried. So just like any leaching process, the solid that is to be processed will undergo drying to ensure that whatever remains is just the solute and the inert solid. So the pigment is produced by precipitation. That's referring to the titanium dioxide and the material as prepared. So when the material was prepared and for the precipitate to be produced, it is contaminated with 1 kilogram of salt solution containing 0.55 kilogram of salt per kilogram of pigment. So the production of 100 kilogram per second of the titanium dioxide really has this presence of this contaminant in the form of a salt solution. So a salt solution meaning it's salt and water. So the amount of the contaminant can be computed, the actual amount based on this ratio that you will have 0.55 kilogram of salt per kilogram of pigment produced. So if we have 100 kilogram per second of pigment, then we can determine the actual contaminant present in the form of the salt. In here, our contaminant, the salt is our solute. So the material is washed countercurrently with water in a number of thickeners arranged in series. So how many thickeners will be required if water is added at a rate of 200 kilograms per second and the solid discharge from each thickener removes zero point 0.5 kilogram of solvent per kilogram of pigment. It requires you to find the number of thickeners with this particular condition, that you're using this much of solvent and that the amount of uh, solvent discharge from the underflows of each of the thickener is 0.5 kilogram per kilogram of pigment. So this much of solvent goes with your solid in the underflow. Another scenario would be what will be the required number of thickeners if the amount of solution removed in this case uh, is dependent on the concentration of the solution. So this is a case of variable underflow. The amount of solution to be removed is a function of the concentration of that same solution. So you can see here two columns. You have here the amount of solution removed for a particular concentration of solution. So concentration, we have kilogram solute per kilogram solution, and amount of solution is kilogram solution per kilogram of pigment. Now, it is to be assumed that the concentrated wash liquor is mixed with the material fed to the first thickener. So meaning the overflow on the first thickener, that's the concentrated wash liquor, is mixed in the agitator together with the solid that will be processed before it's fed to the first thickener. So the illustration actually in this case is similar to this one. The concentrated wash liquid will be mixed together with the solid, in this case not the solution and the lime, but rather the titanium dioxide. The mixture of the two will be the one that will be fed to the first thickener. So I'm just using this illustration in sample problem number 3. But in our case, this would be our countercurrent washing. And we have the first thickener here. We have the H thickener here, equivalent to the nth stage for the previous separation processes discussed. And we have the nth thickener here, equivalent to the last thickener, excuse me, which is represented by capital letter N. in the previous separation process as discussed. So the problem that we are to solve is this one. So I will now go to our board for the solution. So we'll start with the given. So this is our feed having 100 kilograms per second titanium dioxide. So the contaminant in the form of the salt is in the form of a water and salt solution. So we have so 1 kilogram salt solution, and this has 0.55 kilogram salt per kilogram pigment processed. Okay, now we have this. If this is our first thickener, so this must be x sub 1, this must be x sub 2. If this is our H thickener, this would be our H sub x sub H, and this is our last thickener N. This would be the x sub N. So in here we will have solute and solution in the underflow. So we have L1 capital W1, L2 capital W2, L sub H capital W sub H, and this is L sub N capital W sub N. Your solvent is represented by small w sub n plus 1. If it has some solid present on it, that would be, by the way, L sub n plus 1. By the way, class, this is not S because the solute in the underflow is to be presented by S, not L. So we'll change the L's here. The L is for the overflow. So this is S1. This is S sub 2. This is S sub H. And this is S sub N. Now this one, we will have a corresponding overflow here, and that would be small w sub n, and it has this solute L sub n. What enters here, since this is dot dot dot, is I'll place here, place it here. What enters your H thickener in terms of the solvent is W sub H plus 1, and the solute is L sub H plus 1. So for this one, for the overflow from that thickener, it's WH small, and you have LH. This one, this is that would be L3, W3, by the way, so this is continuous already. This is L2, W2, and this is your final wash liquid. okay, that will contain as much of the contaminant salt, which is our solute. So this is L1. The solution is small w sub 1. So this is our illustration for this problem. Now, our wash liquid is pure water. So then this must be 0. And this one is 200 kilograms per second water. What else? So we have the solute here. The solute or the solid will undergo drying after the last washing, and this will be 99.9% titanium dioxide, meaning you have a 0.1% salt remaining in the underflow of your last thickener. It's understood that after drying, all your water will be evaporated. Okay, now what else? So this is our set of given information for this problem. I think everything is in here. Now we have to determine the n, but we have two conditions for the n. So I'd like to put the two conditions on the next sheet. So for letter A, you have like to write it as W prime because it's not the actual solvent or solution. It's just the solvent. So we have this much solvent removed in the underflow per kilogram pigment processed. If this is the scenario, this one is a constant. It's constant for all thickeners that we will have the removal of 0.5 kilogram solvent per kilogram of pigment produced. For letter B, that's when we have a case of variable underflow. And you have this set of data. So we have concentration of solution. So this is in kilogram solute per kilogram solution. So this is this one. And we have amount of solution removed. So this would be kilogram solution per kilogram pigment. So it's dependent on the amount of pigment processed. But nonetheless, the amount of solution removed is also dependent on the concentration of that particular solution in the underflow. So this is a case of variable underflow condition. So you have here a 0, you have a 0.1, a 0.2, a 0.3, a 0.4, and a 0.5. So in here you have a 0.3, and this is incremented by 0.02. So 3, 4, 3, 6, 3, 8, and you have here 40. If you look very closely to this set of data, the increments are uniform for concentration of solution. The increments for the solution removed is also uniform at 0.02. So we can say that the relationship between these two, the amount of solution removed in relation to the concentration of that same solution, is linear because the increments are, shall we say, uniform. But before we process this given information, because it's in letter B, we will process the N, or we will determine the N in the case of the constant underflow condition with this much of solvent being removed per kilogram of pigment processed. So we go to our solution. So for letter A, we need to do our overall material balance on the entire system. And just like what we did with the second sample problem, or rather it's the third sample problem, we'll have it based on the components. Titanium dioxide, the salt, and the water. Okay, these are all having units in kilograms. Okay, so for the feed, for the wash solvent, so we have the feed for the wash solvent, which is small w sub n plus 1, for the slurry, and for the wash liquid in the first thickener, or our final wash liquid, we have w sub 1, small. So for the feed, we have 100 kilograms per second titanium dioxide, and it was mentioned that our contamination is 0.55 kilogram salt per kilogram of pigment. So we will multiply it by 100, that should give us 55. If we have 0.55 of the salt and we have a solution of salt and water, then it follows that the water in this case would be 45. Okay? Now for our solvent is pure, so it doesn't have the titanium dioxide, it does not have the salt, so we only have the water, which is 200. As for our slurry, of course, it will contain our titanium dioxide. It was mentioned that our solid is 99.9% pure titanium dioxide. So meaning, in the last thickener, there's still 0.1% remaining. 0.1% remaining salt that was not removed. So that would be 0.1. And then we have this statement in the problem that 0.5 kilogram of solvent is being removed in the underflow for every kilogram of pigment. So 0.5. So it's the given, actually, the given condition for this constant underflow condition. So let me go back this one. So this will tell us the water present in our slurry, which is 50. So it's dependent only on the amount of pigment processed. Then our final wash water, of course, should not contain the titanium dioxide because that's our inert solid. And just like what we did in our sample problem number 3, the last values here for the two columns will be processed using material balance for the first 3. So you use this one and this one to find the value that you'll place here. So F is entering our system, slurry is leaving our system in terms of the salt present. So the salt in the final wash water, the overflow from the first thickener is 54.9. 55 minus 0.1. This one, so we have here water being 195. Okay. Now we have a formula for R. Since our formula for N is dependent on the R, so we have a formula for R. You have actually 3 choices. You can use any of those depending on what the problem provides you. So in here, we'll use solvent in overflow, discharge, or solvent discharge in overflow over solvent discharge in underflow. And you can see these two. It's a different color. And you can see the two here. Okay, solvent discharge in the overflow, solvent discharge in the underflow. So in that case, we will have a 200 over 50, and they should give us a 4. Okay, now, next thing that we need is the S sub n because it's part of the formula. The S sub n is the solute present in the nth thickener. So we'll have the S sub n is equal to this one. This is your S sub n because this is your slurry from the nth thickener. So that would be 0.1. Now for the present in the feed, solute present in the feed here, we can use the one that is this particular concentration in the overflow of the first thickener because the concentration in the overflow of the first thickener is the same concentration in the solution of the underflow of that same thickener. So we will determine how much of salt entered in the feed based on this ratio of the uh, concentration. So ratio of salt to water, that's the concentration here that we will use in the overflow from the first thickener because this concentration also is the same as that in the underflow solution. So we will use that. So if we have 50 50 kilograms of water removed in each of the thickeners in the underflow, that's 50. How much of salt is present on that will be, in the case of the first thickener, will be based on this concentration ratio because this was also the same as that in the underflow. So we will multiply that by 54.9 divided by 195. So our solute present in the feed, the same solute that leaves our first thickener more or less, is equal to 14. So in here, Colson assumed that the removal of the solute in the first thickener is not as, shall I say, is negligible yet. So it's not as important as the removal in the next thickener. Although we know that the salt that is present in the feed into the first thickener, of course, will be higher than the salt present in the underflow. But in this case, Colson assumed that the removal is just very negligible in terms of the salt solution, primarily because your wash liquid is already concentrated. Concentrated in the sense that it already came from the nth thickener then down to the first thickener. So if it's already saturated, we know that at some point the degree of mass transfer will be not that shall I say, mark. It's not a mark or shall I say, hindi na siya negligible or it's negligible because it's already concentrated. So this is the salt present in our feed. Okay, with this, we can now go to our formula in finding the N. So we have this formula. It was shown to you in the previous recording. F is equal to S sub N over S sub O, which is equal to R minus 1 all over R raised to N plus 1 minus 1. So if we will substitute the information that is given, we have 0.1 over 14, and we have R minus 1. Our R, by the way, our R is 4, so I will place 4 here. So we'll have here a 4 minus 1 over a 4 raised to n plus 1 minus 1. So if we'll process this one here, you will have a 7.14, 3. Times 10 raised to negative 3. And we have a 3 here, and we have a 4 raised to n plus 1 minus 1. You have a 4 raised to n plus 1 minus 1 equal to 420. So 4 raised to n plus 1 is equal to 421. We take ln of both sides, so you have n plus 1 ln of 4 is equal to the ln of 421. So your n here is 3.3588. Now, unlike the other separation processes in leaching, we are to answer in terms of the number of washing thickeners in the form of a whole number. So that our answer should be the next whole number based on our answer. So even if this is not, we cannot round it off, our answer should be 4. So we answered the next higher whole number to our computed number of thickeners. So if it's a constant underflow condition, in this case, the process of determining the number of washing thickeners is easy because we have a formula to use. We are not doing material balance on each of the thickeners, but we are using the formula. So in the case of number 2, it would be a different story. So that would be actually not number 2, but letter B. So I'd like to go to our given for letter B. So this is our letter B. So the amount of solution removed is a function of the concentration of the solution. So if I will have this amount of solution removed represented by y, and this is by x, since y is dependent on x, I need an expression, a linear expression of the relationship of the two. Then later on, I will just change the x and the y. So if you look very closely here, this is our x is 0, and this is our corresponding y. In what you've learned in your geometry, we know that when x is 0, the corresponding answer for the y is the y-intercept. So then we say that our b here is 0.3. So meaning in this equation, the b is 0.3. That leaves us with the slope. We need to determine the slope of the line represented by this set of data. So you can choose any of the pairings here. You can have this one and this one, or you can have somewhere in the beginning or at the end. Doesn't matter, it would be the same slope. So we have slope actually, you've learned that as delta y over delta x. So if you're going to use the data that I have chosen, so you have that, the answer for this is 0.2, or that would be 1/5. Okay. Therefore, we can say that our equation is, so amount of solution removed, if you know, the amount of solution removed is represented by W, amount of solution removed in the underflow. And as a particular thickener is represented by H. So we'll have WH being equal to, we have 0.2, then it's dependent on the concentration of the solution. So concentration is XH. Then we add the y-intercept. So this will be the formula that we will be using in finding the amount of solution leaving in each of our thickeners, because H here could be any thickener based on the concentration of that same solution in that particular thickener. Okay, so the formula that we have there, we will be using. Now, I'll write this particular equation here so we will not have to go back. So for letter B, we're now on letter B. So for letter B, we have WH is equal to 0.2 x sub h plus 0.3. We'll have this as our first equation. Then we know that we have this formula that the amount of solute present in the underflow of a particular thickener is actually the amount of solution in the underflow times the solution concentration. Okay, now in this case, we will have here a 0.3 XH. Oh, that's 0.2. 0.2 XH plus 0.3. This will be multiplied to XH. So the W sub H is multiplied to X sub H. So your SH has another formula now dependent on concentration. So you have 0.20 X sub H squared plus 0.3 X sub H. This is our first, or rather, this is already our second equation. So we need to take note of this formula. We can actually use this formula where SH is computed, solute present is computed based on the concentration of the solution, or we can use this formula depending on where's the ease for you to use, or which is easier for you to use. Okay, now we go to our stepwise determination of the concentration of the solution leaving our underflow for each of our thickener. But before we do that, there's a need for us to determine a formula, a formula that will allow us to determine the concentration of the solution leaving the thickener after H, meaning a formula that will allow you to predict what would be the concentration of the solution leaving the next thickener based on the information in the previous thickener. So I need to be able to have a formula for this. Now, to be able to find this one, actually, we need to have solid content over solution. One. Okay. Now, there must be a big question why this looks like the concentration of the overflow, because L is the solute in the overflow and the small w is the solution in the overflow. Why is this one? So we go back to the principle of leaching, that the concentration of the solution in the overflow is the same concentration of the solution in the underflow, which is actually your X sub H plus 1. So we will be using this. So this is our question mark. So what would be this one? Okay, so what we will do, we will make a material balance on the last, shall I say, H, or shall we say up to the next thickeners. And we will do that based on what we have in the slide. So we'll go back to the slide. I will share you. We'll go back to the slide that we have. So it would be easy and I won't have to draw. So we will have, okay, wait. So go back to the illustration. Okay, this is our X sub 1, X sub H, so what the first thickener, the H thickener, and the N thickener. So we will make a material balance on a certain portion of this, whichever is easier to determine. So in this case, we will have S and SH. We'll use a different color. Okay, so we can have a cut here. since we want to know, we want to able to predict the concentration of the solution in the next thickener given the data in the previous. Okay, so we will cut here. Why cut here? Because this is where you have the H plus 1. We want to be able to predict. Okay, wait. Okay. Now, if we will do our L, or we find through material balance the L sub H plus 1, this one, based on this particular thickener here, okay, we'll have the solute balance. I'll write it here. That way we will not have to write it on our solution. So we'll have the value that is entering in terms of the solute is L sub n plus 1. That's entering. Then we have the SH, the S sub H. That should be equated to the value that is leaving, the S sub n. And this one is also leaving, this particular section, the L sub H plus 1. So again, I will emphasize that we cut through here because we want to include the L sub H plus 1. That way, we will be able to determine the concentration of the solution leaving the thickener after the H thickener. Okay, so we will do prediction of the concentration. So your L sub H plus 1 is equal to, so we just transfer this one here. So you have L sub n plus 1 plus S sub H minus, by the way, this is L sub n, S sub H. This is S sub n, S sub n. So it's hard to distinguish H from the N. Okay, so this is our L sub H plus 1. As for the omega, it's this, we will just follow this particular orientation. So for the omega, or the small w sub H plus 1, that would be the small w sub n plus 1 plus small w sub H minus small w sub n. Now these two we will use in the X sub H plus 1 that we have in our solution. So now I like to determine the value of this and substitute it on our formula. So we go back to our solution and write this particular formula. So that this one, the one that I have shown to you, should be written here. So we will write it here. We'll have the L sub n plus 1 plus S sub H minus S sub n. Then we have small w n plus 1 plus small w h minus capital W sub n. The small w's are for the solution in the overflow. The capital W is for the solution in the underflow. So for now, I don't have yet all the values that I'm going to place here, but we'll just crash out what we don't have. So this one is 0. Okay, we don't have any solute in our solvent entering the last thickener. So this would be simplified in the form S sub H minus S sub n over, we'll have W sub n plus 1 plus W sub H minus capital W sub n. we'll have this as equation 3, because I need to know the things that I need to place here. That way, the things that I can just place, that way I can predict the value of the concentration of the solution in the underflow of the next thickener. So we'll go to the next sheet. So if we do an overall material balance, just basing for 1 unit of titanium oxide processed. So remember, the problem processed 100. So anyway, you can cut it to 1 by dividing everything by 100. So we know that our L sub n plus 1 is already 0, so we'll just write it here. And our solvent, the small wn plus 1, is equal to 2, because that would be 200 divided by 100. And we don't have this because we don't have solute in our solvent. So we have 0, and then we'll have the Sn, the solute in the nth thickener, remember, is 0.1. The contamination, the contamination that remains, because we have a 99.9% pure titanium dioxide. So that 0.1 we divide by 100. So 0.1 we also divide by 100, because we use this one for every unit of titanium dioxide process. So you have 0.001. What else? So we can also have the solution in the feed, and that would be our 1.0, because our feed has a contaminant of this solution, which is 1 kilogram for every kilogram of pigment. So that is the purpose why we have here 1 unit titanium dioxide. That way this one will be 1.0. Okay? Now, the next thing that appears in the formula is the W sub n, the solution that leaves the nth thickener. Now, how do we find the W sub n? So we use the equation for W sub h. You recall, that's our equation. Let's go back. This one. So we'll use that. So you have W sub n is equal to 0.20 x sub n plus 0.3. So in the case of the nth thickener, we'll have a 0.2, and we know that in our nth thickener in the underflow, we have 0.1 of the salt remaining. We have 0.1, and we have 50 of the water that goes with it. Okay, 50 based on the given. So we have the answer here to be equal to 0.3004. Okay, now with that, we can determine the x sub 1. So we now go step by step finding of the concentration of each of the thickener. So for x sub 1, that would be the L sub n plus 1 plus the SO minus the SN all over the W sub n plus 1 plus W sub O minus W sub n. Okay, so we will substitute what we have already. This is a 0, and actually I have written this already in the previous slide, but I'm writing it here for you to easily recall this one. Okay, this is the formula. So x sub h here plus 1 is, if it's x sub 1, then this must be LO, and this must be L, wait. If this is x sub 1, so this must be SO. This is SN. This is really SH, by the way. This is really SN. This is really your solvent. This is your WH, which is your solution in the H thickener. And this is your W sub N. Now, we will determine the X sub 1 in this case. So, the X sub 1 will be used in determining the concentration of the solution in the underflow of the first thickener. So the same principle will apply in the manner we took the X sub H plus 1 here. So this is your equation. Okay, I leave to you to check how this came about, this Ln plus 1 SO and Sn over this. Okay, anyway, it was discussed also a while ago. So just review. It would be better that when you listen to this discussion, you have a piece of paper so you can write on the solution as we go along. Okay, now we will substitute here a 0. This is a 0. For the SO, we have 0.55 here, the solute in the feed. Okay, this is the contaminant salt. And we have the SN. It's also presented in the previous sheet. And we have here 2. And we have for the W sub O1. And in here, we have 0.3004. So you will have an X sub 1, which is 0.203. Now that you have the X sub 1, I'll place an arrow there. You can solve for the S sub 1 knowing the W sub 1. So we'll first determine the W sub 1. So your W sub 1 will be 0.3 plus 0.2 times this, 0.203. And this would be your 0.3406. Once you have this, it was also presented to you. You can find the solute present in the underflow of the first thickener. So this is actually W1X1. So you have 0.3406 times 0.203. So your S1 will be 0.0691. Now, why find S1? Because S1 will be needed together with the W1 will be needed in predicting the next X. And that is the X sub 2. So the X sub 2 will be based on our formula. This is also our formula here. You base it on the X sub H plus 1. So if this is X sub 2, then this one should be W sub 1. Because this is 2, this must be 1. This must be 1. Okay? Now, the N, of course, is fixed as the N for that particular stage. So, your X sub 2 would be negative 0.001 plus S sub 1 all over 1.7 plus W1. So, you're using these two to find the next concentration. So, if you will substitute value, your X sub 2 will be 0.0334. Then you determine W sub 2 and you determine S sub 2 to get X sub 3. Now, W sub 2 is 0.3 plus 0.2 times, of course, this one, the X sub 2. This gives you a value of 0.30668. For the S2, you have W2X2. So you will have 0.30668 times 0.0334. There's also a formula in finding the S other than the multiplying these two. You can also use that one. It was presented to you in the previous sheets. So S2 in this case is 0.011025. Now, when will you stop? So you already have X2, W2S2. Of course, you can determine the X3. The next would be X3. So let's say we'll first solve the X3. So for the X3, you need negative 001 plus this time, this is S2. And you have 1.7 plus W2. So in order to find this, you need the previous data from the previous thickener. So if you will substitute value, your X3 would be 0.00447. Now, when will you keep this? When will you keep going? So remember that you need to keep going until you reach a concentration that is acceptable based on the given in the problem. So meaning you need to find the x sub n. So a while ago, I gave you the x sub n. I'm not sure if I have given to you the formula for the x sub n. Let's check. It's the s sub h that I gave. So for the s sub n, or rather the x sub n, that would be the s sub n over, that's n plus a capital W sub n. It's so easy to get confused with the h. So for the s sub n, it's already determined there. It's 0.001. We already determined that. And the W sub n is, let's check if I have shown to you how to determine the W sub n. This one, the 0.3004. 0.3004. So your answer for the x sub n is 0.0033. What's the purpose of this? I'd like to underline this one. What's the purpose of the x sub n? This will be like similar to iteration or similar to looping in your C++, wherein you stop what you're doing until a particular condition is reached in which your the value that you are getting is acceptable in terms of the objective of the problem. So our objective that our nth thickener will have this concentration in the underflow. Now since our here, we are already on the X3, this one, I like to use the red. This one is greater than 0.0033, then you need to continue because we only stop when the concentration that we have solved for the next thickener will be either equal to or lesser than this one. Equal to or lesser than this one. So then that needs us to determine the W3 and the S sub 3 and check what would be the X sub 4. So for W3, we have 0.2 times 0.00447. This is our X sub 3 plus 0.3. So your W3 will have 0.30089. That's W3. Then we need also the S3. So for the S3, it's W3X3. So if we will substitute the values that we have on top, your S3 will be 0.0013. Now we can check, we can solve for X sub 4. So we'll have negative 0.001 plus S3 over 1.7 plus W3. So you'll have negative 0.001 plus 0.0013 over 1.7 plus 0.30089. So your x sub 4 in this sense would be now, if you will process this one, is 0.00015. That one, this value is already less than this x sub n, which is 0.0033. Therefore, we should have number of thickeners which is equal to 4, just like in letter A. Why? Because if you'll only have until the third, the concentration that we'll be getting is still greater than 0.003, which we have predetermined already based on this particular formula. Okay? So it's really very tedious to determine the number of stages or the number of thickeners for leaching if the problem is variable underflow. If it's constant underflow condition, it's much easier because you'll have a formula that you can substitute values, and then that's it. In here, you have to keep on going until the concentration of the solution in a particular thickener that you are calculating is already equal to or less than the concentration that you have predetermined for the thickener. Okay, so this is our answer for this problem. So this ends already the topic for leaching. Actually, if you have read your book in John Copley's, there's still a particular topic on leaching which determines the minimum solvent requirement. The problem with that particular topic is there's no other solution that I can find that will make it analytical. So your solution is dependent on the equilibrium diagram, and it's really graphical. So the only graphical, you cannot solve it unless you have the graph with you. So I leave that to you to study just in case you want to know how it's being done. But in terms of the likelihood of it coming out in your board exam, it's nil. So though it's really like zero probability because you're not doing graphical technique in the board exam. So since we already have anyway procedures that are analytical, we utilize those. We discuss the graphical technique whenever possible if the equilibrium diagrams that we will be using for the systems that are given to us are readily available. Just like in the case of distillation, wherein we have several equilibrium diagrams for the systems that are provided. In the case of leaching, it's only very limited to the system of isopropyl ether, acetic acid, water, something like that. And it's all the sample that you will be seeing in your book by John Copley's. Okay, so I hope you've learned something out of this particular sample problem. 4 sample problems on leaching, one sample problem which is graphical, you can read in John Copley's. Okay, I'll stop sharing now. And thank you for listening, class.